Welcome to another edition of Coonrod's Corner, brought to you by the Rogers Corporation. Today's topic: why thermal coefficient of dielectric constant circuit performance testing is critical in order to understand environmental influences. Now here's your host, John Coonrod.
Hello, welcome to Coonrod's Corner. My name is John Coonrod, and I'm a Technical Marketing Manager for Rogers Corporation. Today I'm going to be talking about thermal coefficient of dielectric constant, TCDk, more specifically testing TCDk in circuit form and how understanding circuit performance can be very critical to understand how the circuit would behave in different environments. So TCDk is really a property that all materials have. It's essentially how much the dielectric constant will change with a change in temperature. And some materials are better and others are worse, of course, with TCDk, really based on the formulation. But as a general rule, a TCDk value of 50 parts per million per degree C is considered good. And ideal would be 0 parts per million per degree C. That would be an ideal TCDk, basically saying that the dk does not change with a change in temperature. So let's go ahead and take a look at some TCDk curves of different materials and make some comparisons. Shown here are several different TCDk curves for different materials. To begin with, the brown curve is a sanity check, and that's really FR4. So FR4 is a material that's not considered good for TCDk, and I wanted to give you a reference for what a poor TCDk looks like, and that's really this brown curve. Now the other curves on here are all good TCDKs, and a couple of them extremely good. Now the purple curve is interesting because you get this transition around room temperature, and that's normal for PTFE. Now there's things that can be done in the formulation of a PTFE-based laminate to minimize that. As a matter of fact, the very dark blue curve that's almost ideal right at the 1.0 line on the y-axis, and by the way, the y-axis is normalized dk at room temperature, so 1.0 would be perfect. So the dark blue line is actually our RO3003 materials, and it has a TCDk of 3 parts per million per degree C. And that's about as close to perfect as you can get. So this is actually a change in dk with a change in temperature, and the y-axis is normalized dk as I've mentioned. X-axis is temperature going from minus 50 C to plus 150 C. Rogers Corporation has defined a test method where we can test circuits for TCDk. So the previous chart was actually looking at TCDk for the raw material itself with a clamped fixture. But the process for actually testing a circuit for TCDk is using microstrip transmission lines, and specifically using the microstrip differential phase length method. So we are able to get circuit properties out of this type of testing, such as insertion loss, phase response, group delay, impedance, and you can see how these different circuit properties change with a change in temperature. And that can be very advantageous to the designer to understand how their circuit's going to behave in the field where you have environments that are changing. Shown here is the basic procedure of how we do the TCDk testing. So again, that's TCDk testing in circuit form, and we are using the microstrip differential phase length method, and what that is basically testing two circuits that are identical in every way except their physical length is different by a ratio about 4:1. So these are microstrip transmission lines, 50 ohms, and we test them for insertion loss and also phase difference. Now for this particular test, what we do is we start off with the short circuit being placed on a heat block that is essentially at room temperature to begin with, and then we hook up everything, the cables, connectors, we make sure we have a good return loss, good sweeps, then we collect the data at room temperature. Then without moving anything or disconnecting anything, just turn on the heat block, and we heat it up to 65 degrees C, and then once we have a good thermal equilibrium at 65 degrees C, we will collect more information with the P&A. And then finally, we'll move up to a higher temperature. We'll turn up the heat block to 125 degrees C, make sure it's at a good thermal equilibrium, and then collect data from the P&A at that temperature. So that's what we do on the short circuit. Once we're done with that, we take all that apart and we put a larger heat block on and the larger circuit, and we do the exact same procedure all over again. And that's done at the different temperatures, room temperature, 65 degrees C and 125 degrees C, and then we collect all the circuit information at those different temperatures. Recently, we've done several different studies using the circuit TCDk testing to look at some of the properties of the circuit and the materials and how they react to different temperatures. Now, one thing that was interesting is, and you can see this in previous Coonrod Corner videos, is that we know that a thinner circuit is more dominated in RF performance by conductor effects. and a thicker circuit is more dominated for RF performance by the dielectric effects. So thinner circuits more impacted by the conductor effects, a thicker circuit's more impacted by the dielectric effects. So as part of our study, what we wanted to do was see if the dielectric actually does dominate for TCDk and temperature differences for a thicker circuit compared to a thin circuit. So as part of our study, we looked at the same material, same circuit, except a thin laminate and a thick laminate, and we were wanting to see if the TCDk had a bigger influence on the RF performance for the thicker circuit. Now, on the other side of this, we were looking at conductor effects. Now, a thinner circuit's more dominated by the conductor effects. So as part of the study, we used the same material, but we used two different types of copper on a very thin laminate. And then we compared differences at different temperatures to see if we saw a difference due to conductor effects. So we know that as the copper heats up, it does change conductivity, and there is some suggestion that a change in conductivity can have an effect on phase response. So we were looking for that as well. And as part of the study, we also looked at materials that had good TCDk and also materials with poor TCDk. Shown here is two graphs showing the circuit TCDk behavior of two different circuits using the exact same material. This is using the RT Duroid 5880 laminate. Now the RT Duroid laminate 5880 has been around for many years. It has extremely good electrical performance. However, one drawback is it's got poor TCDk. And that's what we're going to use for an example here to begin with before we compare it to another material with very good TCDk. So you can see the curves are at room temperature, 65C and 125C, and there's a difference in dk here and difference in phase angle. What's interesting is the chart to the left, upper left, is for a 5 mil thick substrate. The chart on the bottom right is for a 10 mil thick substrate, and you can in fact see differences between the thin and the thick circuit, where the thicker circuit is more impacted by the change in temperature than the thinner circuit. So it does verify that a thicker circuit, which is dominated by dielectric effects, is affected by the TCDk more than a thinner circuit. The comparisons shown here are still the same material, RT Duroid 5880, and in this case they're the same thickness for substrate, 5 mils thick, so it is thin, and the conductor effects are going to be exaggerated. But in this case, what we did is we used a material with two different types of copper. So we had ED copper on one set of circuits and rolled copper on another set of circuits. And what we found after going through the different temperature testing, that there was absolutely no difference between these two sets of circuits, that the TCDk and the temperature changes had no effect on these two different circuits. So even though it's the same material with a poor TCDk, when you have differences of copper only, it looks like the copper change due to conductivity and being heated is not significant, and it was not picked up at all in this test. The charts shown here are actually the same charts as the previous, except using a different material. Now we're using a material that has extremely good TCDk. This is the RO3003 materials, 5 mil thick, with rolled copper and ED copper, so we're looking at differences in copper, but you can see in the numbers here, there really is no difference at all. So a material with a very tightly controlled TCDk, which this is, you can see that the difference between room temperature, 65C and 125C, is really insignificant. It's really within the measurement noise of this test method. This concludes this session of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you're not already a member, join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.